Welcome back to Advent of Code 2025, day 10. So we're kind of fallen behind in keeping up with these problems because I had to travel and then I was just too tired yesterday. Uh, so, but I don't want to fall behind in terms of the days, so we'll try and do 10 today and then maybe I'll take a lunch break and then maybe come back and try and finish off 9 because I already started that, and then 8. 9 was a bit of a mess, but with a fresh mindset, maybe I can clean it up. I mean, I have the idea. Doesn't matter. Let's focus on day 10. Hello, DJ. All right, so day 10. It's been out for just an hour and 20 minutes. Factory. Okay, it looks like some sort of optimization of some sort of bin packing problem. Just across the hall you find a large factory. Oh, where's the music? All right. Factory. Fortunately, the elves here have plenty of time to decorate. Unfortunately, it's because the factory machines are all offline, and none of the elves can figure out the initialization procedure. The elves do have the manual for the machines, but the section detailing the initialization procedure was eaten by a Shiba Inu. We'll let the Shiba off for being adorable. All that remains of the manual are some indicator light diagrams, button wiring schematics, and joltage requirements for each machine. For example, the manual describes one machine per line. Each line contains a single indicator light diagram in square brackets, one or more button wiring schematics, and joltage requirements in curly braces. Oh boy, okay. I was going to use regular expressions for this, but we can manage fine just by pausing it. To start a machine, its indicator lights must match those shown in the diagram. So dot is off, hash is on. The machine has the number of indicator lights shown, but its indicator lights are all off to begin with. Alright. So an indicator light diagram like that means that the machine has 4 indicator lights which are initially off, and the goal is to simultaneously configure the first light to be off, the second light to be on, the third light to be on, and the fourth to be off. Alright. Oh, it's one of these light switching puzzles where each switch does multiple things. Twitch player, have you forgotten how to list video resolutions by size? Oh, is it not offering encoding options? That's weird. Usually it does, but I think at busy times on Twitch they deny that to affiliates and reserve it for partners. It's displaying... Oh, it is showing the encoding options, it's just not showing them in order. Okay. Also, what is 160? 160 is what I'm playing this audio video at. Which, because it doesn't affect the audio. But yeah, a 160 is barely watchable. Oh, that's 144. Well, no, wait. Yeah, 144. I guess that's technically lower. You can toggle the state of indicator lights by pushing any of the listed buttons. Each button lists which indicator lights it toggles. Alright. Alright, I get it then. Alright. So button wiring schematic like 034 means that each time you push that button, the first, fourth, and fifth indicator lights would all toggle between on and off. Because none of the machines are running, the joltage requirements are irrelevant and can be safely ignored. You need to determine the fewest total presses required to correctly configure all indicator lights for all machines in your list. You could press the first 3 buttons once each. You could press 1-3 once and 2-3 once and 0-1 twice. You could press all of the buttons except 1-3 once each, a total of 5 button presses. Alright. Hello, Amara. Okay, so first of all, because these are just toggling individual lights, you only ever need to press a button once at most. Like, if you're pressing it twice, it's the same as if you never pressed it, right? So this and 0-1 twice is obsolete, surely. Alright, so really it's just a power set. We want to find which of these we press once and find the minimal subset. It's just a minimal subset. Well, okay, so we can iterate through all the... I don't know, how big is the input? Well, there's probably ways to be smart about it. It's a bit like a Sudoku. You can find ones which absolutely must be pressed. For example, well, this one's pretty evenly spread, but... second machine... okay, I think I get the problem. So the first part is really just, ooh, okay, how big are these? Yeah, we can do 2 to the power of number of buttons, I suppose. Wait, what's the last thing? Is that... oh, that's for part 2, okay. Okay, I think it's just... really just brute force then. Well, just a bit simpler than brute force because we're not pressing buttons multiple times each. Alright. Oh boy, problem 9. We'll have to get back to that sometime. Just trying to copy some code here. Guess we can solve the problems as we read them in. I could use regular expressions for this. I mean, it's... I can't be bothered to whip out regular expressions. We can just find the square bracket. So Um, so we want I1 equals line dot find closing square bracket, and with that we want that pattern there. So pattern equals line from 1 up to I1. And then light's goal equals a list, and then for Z character in enumerate pattern, if character is a hash, then we want that in our light's goal. Yeah, okay, that's that pattern extracted, and then this bit I1. So line from, let's say, I1 plus 2 on 2 onwards. Dot split on the spaces, and then we just ignore the last one because that's like something for part 2, I think. So buttons equals that. Let's just discard the last one. Alright. Or just say tokens. Buttons equals... Could we not just eval? These are tuples, basically. Can we just eval this? Oh, no, because they're not comma separated. Oh, that's fine. We'll just, well, we can eval that string, and that will give us... it'll probably work. For token in... tokens... buttons dot append eval... Just evaluate the string, and that should... be the tuple. Okay. And then let's just see what this looks like. So we've got a lights goal and buttons. So that's the goal, and that's what the buttons do. Oh. Can't have an integer by itself. Let's just... Okay, if you put a comma at the end of a tuple, it doesn't change it. But if you put a comma at the end of these, it fixes it to become a tuple. So we could... Okay, this is a hack. Token and tokens. So... Scrap the last character. Add a comma. And a brackets. That should work. So do we have solo tuples? Singletons? Yeah. Okay. So that's the inputs basically, and we want to probably do this outside here. Define. So what is the goal? We want to fewest button presses. All right. Define get optimal presses. So we've got a goal, and we've got buttons. We're just wrap this up as a tuple. Okay. And then result 1. Okay. Oops. Okay, right. So now we need to just do this method up here. So we've got a goal, we've got buttons. So I think we just try every combination of pressing the buttons. So, so which of the many cheaty methods in IterTools does this? It's going to be IterTools dot let's look this up. Products. No, it's it's none of these. What is it? It's we want without. Hang on. Cartesian product nested. We don't want this number here, do we? Combinations. If I do combinations, so it's combinations, is it? Rnth tuples in sorted order, no repeated elements. Yeah, combinations, but we don't supply the 2. It's just any length. So it's essentially the subset. Let me just try it and see what it looks like. For R in combinations buttons in R, there's going to be a whole bunch of text. Combinations missing requirement R. Wait, we need R? No, it's not combinations we want. And I'm still in the browser. Hang on. What? I don't remember what the method is. Maybe it's not even in ITtools. Let's just Google this. Python. Get all subsets of a sequence. That's what we want, right? Get all subsets. It's combinations. We have to do it for R in range. I could have sworn there was a... Okay, fine, I can do that. That's easy. But I could have sworn there was a... one function. I guess... Oh, okay, that makes sense. I guess there's no... He didn't add a function that would actually get all subsets to Python, because that would be pointless, because in practice you don't do that, because that's exponential. The same reason we don't have the equivalent of sum for product, because if you multiply like a bunch of numbers together, eventually they get too big. So it's just a silly function to have only for toy problems like this. Okay, so we just do a for loop. For k in range length of buttons +1, we could have all of them pressed. For R in combinations buttons K. At least no assembly problems this year. Well, we don't know yet. I'm sure he'll throw in 1. Botones. Okay, stop. Okay. Let me just... Alright, so the last one is... Let me just look at the last one. Alright, I think that's fine. Alright, so for that combination... Alright, so we want... Best... Okay. 0 is... No, we don't return 0. Well, okay, there's no sensible default. Best equals... length of buttons. Like, in the worst case, we press every button. Is it always possible? Yeah, it must be. Alright, so, and we want to include 0, because it may be that you don't press any buttons, and the goal is to just have them all off. I don't think they'll actually give that pattern, but in theory we should include that. So, with that, okay. For B in So let's say subset in, for B in subset. So lights equals oh, what's the best way to do this? Dictionary? Just lights equals I 0 meaning the light is off, for I in range length of goal. That's how many lights there are. For B, I'm just waiting for day 12 to take like 5 days to complete. Well, if it takes like 13 days, it'll take us until Christmas Day, so he'd have kept the pattern going. So for B in subset, okay, so we've got a button. It triggers each of these lights. So for running out of variables, X in B, lights X equals 1 minus lights X, or maybe we should use booleans. Is that nicer? Yeah, okay. Okay, so at this point, we want to see if that matches the goal. So, lit lights equals X for X in range. I should really. It's fine. Length goal. If lights X, so the light is on. Lit lights is that. That's a set. If or I don't know. I'm gonna make this a tuple. It's doing it starting from 0, so it should be sorted. If lit lights is goal, so goal, should that look the same? That's sorted tuple, yeah, I think so. If lit lights equals goal, then we have a way of turning on the goal lights on. Also, best shouldn't be length of buttons. It should be length of buttons plus 1, because it doesn't really matter. Because essentially this is an invalid best. All right. If lit lights equals goal, best equals minimum of best and length of Okay, there's an optimization here. So because we're looking for subsets in increasing size... Alright, well, anyway. Let's just finish this off first. Hopefully next year he can get them all done or get some help. I think he's decided this is going to be the length going forward. And he does get a lot of help, but he wants to always write the problems himself. But he does get a lot of help in testing and stuff. But I'm pretty sure he writes all the problems himself, and I think it just takes too long. He spends months doing this. Alright, so, oh, I lost my train of thought. Where was I? Best length of subset, right? Yeah. Alright, now, what we can also do is, if k is greater or equal to best, like, we're now looking at big subsets, but we've already found a solution which is smaller, then we just return best. Like, we know that none of those bigger ones will be any better. And if we go through... If we get here, like generally we're gonna exit early always here, but okay. Okay, that's a mouthful. It's probably gonna break. Key error 2. Error 2. X is 2. X 2 is not in there. What? Oh, goal is... Ah, bollocks. Alright. There is a issue here, is that because we are just storing the list of ones we want on, we forget how many lights there are altogether, and we don't actually have a record of that. So instead we should just have the actual pattern. So let's do Alright, how about we just use the pattern itself, except change it to zeros and ones or something. So lights goal equals, let's say, one if car is hash, else. Or we'll just use the boolean. Car equals hash for car in pattern. That's simple enough. Get rid of all this. That's the tuple. Alright, so now goal is just like false, true, 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 false, whatever. So length of goal makes sense now. So lit lights is just gonna be... It's just gonna be lights X. Alright, try that. 571. Alright, well... Let's see. If it feels like it's about the right magnitude... Oops. Okay, nice. It worked. Part 2. All of the machines are starting to come online. Now it's time to worry about the joltage requirements. Oh, great. Each machine needs to be configured to exactly the specified joltage levels to function properly. Below the buttons on each machine is a big lever that you can use to switch the buttons from configuring the indicator lights to increasing the joltage levels. Okay, fine. The machines each have a set of numeric counters tracking its joltage levels. One counter per joltage requirement. The counters are all initially set to 0. So, for example, this one means the machine has 4 counters, which are initially 0. And that the goal is to simultaneously configure the first counter to be 3, second counter to be 5. Third to be 4 and 4 to be 7. Okay. The button wiring schematics are still relevant. In this new joltage configuration mode, each button now indicates which counters it affects, where 0 means the first counter, 1 means the second counter, and so on. When you push a button, each listed counter is increased by 1. Wait, so are we don't care about the lights anymore? I guess not. So a button wiring schematic like 1-3 means each time you push that button, second and fourth counters would each increase by 1. So you want the fewest total presses. So it's like we're now trying to sum a bunch of vectors of zeros and ones. So it's oh man. So generating the full possibilities is much bigger now. Okay, so looking at the first example. So 0 wants to increase, the counter 0 wants to increase to 3. So the number of times we press these buttons has got to sum to 3, essentially. So we could do like 3 of those, or 1 of those and 2 of those, and so on. Interesting. That's a way of, like, breaking it up, I suppose. One way to do this is by pressing 3 once, 1, 3, 3 times. That gets 4 for that, and that adds 3 to that. All right. So immediately, I think a way of breaking this down is to look at. So for example, like I said, with 0, counter 0, we want to make that 3. So we know that these have to be pressed 3 times, like broken up in some way. So for every possibility, every possible way of pressing these, that spawns a whole new subproblem where we've now reached the target with 0. So we delete all those buttons and focus only on what's remaining and what's remaining here. But of course we've got some residual like voltage from those button presses, and then we solve that subproblem. So we're trying to meet that target. So for example, if we press this 3 times, that would hit that target. We cut that off, but we've also added 3 to counter 2. So then we're trying to solve the problem of 5, 1, 7 with those buttons, right? Which is a subproblem. I maybe we should start with, just to make the numbers cleaner, we should start with the highest number. So get rid of that counter, because that then we don't have to renumber them. Okay, so if we started with 3, which is that one, we find all ways of pressing the 3's buttons until we make 7. So for each possibility, we spawn the subproblem where we only look at these 3 numbers, and we don't have to renumber, so we can discard these buttons altogether. We're left with these buttons and these targets, and if they're negative or something, then that's actually impossible. I guess I could try that. That seems to be the clearest, like, and then throw in some memorization, and let's try it then. So that is that. Get rid of that. So we've got the buttons. And so what was the word they used to describe here? Joltage. joltage goal, I suppose. Joltage goal equals, so it's going to be, take the last token, tokens -1, so that's got curly brackets. Let's just throw in an eval here. So tokens goal from 1 up to -1, so we kind of just take the inner section and then just eval with, we've got an opening bracket, we have the inner stuff, and then throw a comma and that, just in case it's like a single thing. Does it always have a counter for every? Are they listing every yeah, I think so. Okay. All right. So we want another method here. Get optimal presses. Let's just say joltage. So we've got goal and buttons again, but this time we're gonna like do recursive, I guess. So goal is given as a they're all given as tuples. Okay. 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 My music stopped. Okay, so we would have memorized, I suppose. Let me just print what these looks like. Print goal buttons. Okay, so it's like that's the goal. Those are the buttons. We want buttons to be a tuple, really. Everything should be tuples. Buttons equals. Okay, so we do buttons equals tuple buttons. Okay, so that should still work. Okay. So yeah. So now we've got a goal. Wait, what? Hang on. I don't think we've got the right tokens here. Ah, we're cutting off the last one, aren't we? Oh, damn. That'll be why. Take that off. Do that. There we go. That makes sense. All right. Memorizations, I don't know how much it will help because there's a lot of possibilities here. Okay, so my idea is we start with the rightmost button and try to hit that target. Oh, I'm really hungry now. Need to solve the problem quickly so I can go get a lunch break and then come back with day 9 or something. So the counter I'm interested in is the last one. So let's say counter equals length of goal minus 1. Okay. So we want to just extract the buttons that involve that counter. Relevant buttons equals that. For button in buttons, if counter in button relevant. Oh, we can relevant button equals, let's say, button for button in buttons if counter in button. So now we want to just brute force all the possible ways of pressing these buttons, I suppose. So the number of presses is exactly goal counter, that number. Okay, so we're allowed to press these buttons, some combination of them, a total of presses times, and work with that subproblem. Alright, what's the Python itertools thing that does this? I suppose it's gonna be like let me have a look at the itertools stuff. Maybe it's not. No, we don't want to actually iterate over them all. We just want to split the number presses into parts, don't we? Oh, okay, what's the way, how do you do that cleanly? Probably another itertools thing, but there's so many methods here. It's like Python, it's like Get all tuples of integers that sum to a target. What is the is combinations with the placement? Like, let me look at that again. Yeah, but we don't actually, no, we don't want to do that. It's partitioning, yeah, that's what we're doing. Python, so we're trying to partition a number into like specific number of parts. That's what we're trying to do, aren't we? Recursion, I guess we'll have to use recursion. I'll have a whole new method here. All partitions of n with length k with 1 in order of least to greatest. Suppose this might length of partitions. Did you beat part 1? Yeah, I've done part 1. Wasn't too bad. Alright, we'll just copy this method because someone's done this partition thing. This is just like a subroutine we want. Oh, that looks good. Except we don't need to... We've got our own memoir. Oh, Python has memoirs built in, so... This was 2013. Alright, let's try this. So we've got a routine here. So we're partitioning a number n into k parts. What's pre? Oh my god, still using X range. Wait, what? Alright, let's not use this one. Let's use a different one. Use this. We don't actually, I don't see why you would even need to cache. Okay. L is the minimum partition element size. So we want L equals 0, I suppose. So let's test this. Print partition. So we want print list of partition function. Say split the number 5 into 3 parts. characters raise stop iteration. What? Length of partitions. Does it just not like me casting it to a list? Should we just say 4p in addition function print p? Stop iteration. What? So it did 005. 0 is 0 valid? 0 is a number we want to allow. If k is less than 1. Okay, if k equals 1, if n... What's wrong? Ugh. So it started with 005, that's valid. And then... Wait, no. Yeah, 005. And then it crashed. Let's try another one. Or just write it myself. I think... Why are they raising stop iteration? Okay, let's return. I think this is probably because they were using Python 2 for this, I think. Return. Return. There we go. 005, 014, 023. 113. That's not all of them. I don't think this is actually what we're trying to do. Oh, they're looking for unique. Alright, let's just write it ourselves. We'll just tweak this. So alright, this is just generating all ordered partitions. We want unordered, so we need to say... K is 1. That's fine. If for I in range L to n plus 1. For result input... I would think this is right, isn't it? We just don't want to return. Why are we returning? When we yield... Hang on. So... Alright, we don't need L. We're always allowing it to be... Oh, no, we do need L. Hang on. Result in partition function. Ah! That's the problem. Okay, we don't want L, actually. L is always 0. We're always allowed to have 0. Let's take that out. Okay, try that. L. N is greater or equal to... Zero, I suppose. Okay. Do we get all... Yeah, we do. It looks like it. Okay, okay, okay. We've got a way of partitioning a number into parts. Alright. So... we want to... For P in partition function, the number of presses into length of relevant buttons. Okay. So this will tell us how many times to press each button. So we've got a... So P is a tuple saying press this button once, this button this many times, this button this many times. Okay, so... Jolts equals... Zero. Okay, start with that many jolts. For I so P looks like, okay, let's say I num in enumerate key. So I is telling us which button to press. And num is telling us how many times to press it. So we take the button in relevant buttons. So button equals relevant buttons I. Okay. For I don't know, K in button, we want to increase that voltage num times. So jolts K plus equal num. Alright, so if we've done all that, for all of that, then we've basically pressed a bunch of buttons, according to this. And what we should end up with is exactly the right number of jolts for this one counter we're focused on. Okay. So the goal for that counter should be hit. We've got a bunch of residual jolts, and so we subtract that from the goal. Now, if any of the new goal numbers are negative, that means this is impossible. Okay. Best equals none, I suppose. I'm trying to find the fewest presses, so okay. So we pressed the relevant buttons a number of times. We've now hit that goal. Now we need to just call the subroutine on the remaining buttons. So new goal equals, let's say, list of goal up to, and excluding the last one. And then we need to subtract the jolts. So for I in enumerate jolts, new goal, I take away that amount of jolts to see what's left. If new goal is less than 0, oh, don't do that check here. It's whatever, just subtract all the jolts. Alright. If any num less than 0 for num in new goal, then this is an invalid P. So continue. Let's move on to the next one. Okay. So now we've got a new goal. New goal equals, let's say, tuple of new goal. Alright, DIJ, see you later. Okay, so that's the new goal. And the buttons, we got to remove some of the buttons, so... essentially we do this. New buttons equals button tuple button for button in buttons if counter not in button. So we want to exclude all the ones that affect that particular counter, because we never press those again. We press them the exact number of times. Okay. So we solve the subproblem. So we now want to call get optimal joltage on this new goal, new set of buttons. I can't think of variables. Z equals get optimal joltage, new goal, new buttons. If Z is none, that means it was impossible to solve. So we continue to the next P. But if we actually got a number, then we've actually found a solution here. So best, if best is none or best is, okay, so num presses equals, so we pressed these buttons that many times. Plus, because that's fixed, plus Z. Z is the optimal solution to that subproblem. Num presses equals presses plus Z. Num presses. Then the new best is num presses. Okay. And then after all that, we return best. We'll make sure we cache this. Hopefully there's a lot of cache hits, I don't know. And then... yeah. Try running it and see. Dict object is not callable. Wait, we've... line cache? What was that? No, it's not cache. What's it called again? I can never remember this. Functools.cache. Alright. Or just from functools import cache. Alright, just try running it then. List index out of range. Wonderful. Ah, because we're trying to subtract. Okay. This particular counter is out of range, so we want to skip that one. So I num in enumerate jolts. I mean, we don't. We don't need to include that one, so for I num enumerate P. If K is not equal to like counter, because we don't actually care about that one. We know that counter will get pressed the exact correct number of times. Alright. None. So if it's impossible, is it always possible? Should always be possible. Yeah, should always be possible. Okay. Huh. There might be some base cases, like if the goal is empty. Like, if all x is 0 for x in goal, then return 0, because we solved it. I don't know if that's something we're missing here. And if it's not, then if not buttons, then that's impossible, because we have to have a button to actually hit a goal. I think that avoided that problem. Why are we doing that? Take that out. Alright, we need to see how much progress we're making here. Are we actually getting results? Okay. We got 45 for the first one. Boy, some of these are gonna take ages. Oh, because these are big numbers. There's got to be a way to... We should really... Be starting with the buttons. Oh. Well, now we're making some progress. How many have we got to get through? 199? We can do it if we just leave this running. It's just some of these big ones. Oh, look at that last one. We got the 200s. That's gonna be nasty. Oh, great. It didn't find a solution for this one. Well, I mean, we've got to try the example input now. Okay, 10, 22. Were those two correct? 10. No, next one should be 12, not 22. Okay. Just looking through this again. Jholtz equals 0. I num in a numeric P. Okay. Z equals get optimal joltage of new wells, new buttons. If Z is none, continue. So that's not solvable. Num presses equals presses plus Z. So the base cases. Yeah, if all the goals are hit, the goal is empty. That's probably what we were having as well. If that's an empty list, then that's also solved. And if there's no buttons, then it can't be solved. Oh, 12 was right. This is not... It's 12, not 22, because this is accumulating. So we actually solved the first two correctly. Okay, that's good. But we couldn't solve the third one. Alright, that's more promising then. Interesting. Yeah, why are we printing? Okay, so... Okay, 10, 12, and then... Okay. So... Let's see how far we're getting into this then. Okay, so... Also, get rid of these two problems. Just focus on that last one. Okay, so... We start with this goal. 10, 11, 11, 5, 10, 5. 10, 11, 11, 5, 10, 5. And we've got these buttons to press. Yeah. And we go for... this last one here. 0, 1, 2, 3, 4. So 4. So we look at all the buttons with 4 in them. There's 3 of them. And we try all possible ways of pressing them. So for example, if we were to press... I think because of the partition, press this one. Wait, what? 0, 1, 2, 3, 4, 5. Oh yeah, no. 5. We want to press... We want to hit this target here. And the only button with 5 in it is this one. So we press that one a total of 5 times. So that means 0, 1, 2, and 4 all get hit 5 times. So the goal has now become 5, 6, 6. That one's unaffected. 5. So far so good. And then all we're left with is these 3 buttons. We're not allowed to ever press this one again. Okay, that looks good so far. Then we want to hit 4. Hit this goal. So we have to try all ways of pressing these 2. One such way is to press this one 5 times. And if we do that, we hit the goal for 0. We don't affect 1 or 2. We actually hit the goal for 3. And if we take those out, so we have to solve this subproblem here. Interesting. But that's trivial, isn't it? Why is it not solving that subproblem? Oh, hang on. I didn't consider the case where we've already hit this goal. Interesting. So we've already hit this goal. This for loop is redundant, and we never actually do any of this logic. So if we hit the goal, we actually have to deal with it there and then. So if okay, so counter relevant buttons, presses, blah blah blah. Okay, best equals none. If presses equals 0, so it's redundantly met. We've met the target redundantly. All right. In that case, we don't have to do any of this, and we just say... Basically, we have to say new goal equals that. New goal equals tuple goal that. New buttons equals basically that. We don't have to do this this is always the same. And so is this. Hang on, so take this line out. So we return get optimal joltage of new goal, new buttons. What on earth? Otherwise we do that. Try that. 11! Alright, I think it works for the example inputs. Let's just check that now. So print optimal. Okay, just don't print those right now. But don't print all this stuff. $10, $12, $11. That is correct. 10, 12, 11. Alright, solved it for the example input. We weren't handling edge cases. These edge cases aren't really... Well, they're covered now. Are there any other edge cases? Not really. Like, if this can't be -1 because we're already checking that. Alright, let's do the big one. So ultimately we want these two. This is probably going to take a while. Print 3. I have to start. 45. Oh man. I think it's correct now. I have to wait for 199 things to be done, but some of them are going to take a long time because these numbers are big, and that's not even that bad. Like, look, it gets worse. It really depends on the button arrangements. Look at that. That's going to be crazy, but I don't know. Like, what could be better? Like we might not need to do recursion. Like, we could just fully partition the target. Wait, no. I mean, there's probably a lot of cases where we can see early on that we're going to exceed We've done 8. We need to do 200. I don't know. I'll just leave this to run. I mean, what else can... I would like to know which line I'm on. Should I do that? It doesn't matter, we'll just let it run. Are there any particularly trolly ones? See, these were all numbers under 100, and now we're getting bigger numbers down here, so this is going to be a problem. Okay. I mean, it looks like this will work. So we're on 10 right now. That's some big numbers, but... So 9 was instant, even though the numbers are big, but I guess the button arrangement... When you have singletons, that makes it a lot easier. Alright, I mean, what could actually be done to optimize this? Maybe... Like when you see things like 4... I don't know. When you see singletons, but you don't always have singletons, so there's no point worrying about singletons. Like maybe you should start with the counter, which has the fewest number of buttons, because then you're more restricted. Not as many branches. I don't know. This is kind of like an algebra problem. We're trying to see how many... Like if we took a number, say 100, or okay, so let's look at this last problem. There's 225, so we know there must be at least 225 button presses. And minimum 225, maximum sum of all these numbers, essentially. So we know the correct answer is between 225 and the sum of these. So for a given number, we could partition that number into the number of buttons, but that's too many. Partitioning is what's expensive, so the reason I'm doing this is because it partitions into a smaller number of buttons. So trying to isolate one particular counter and then take that out of the equation. Oh, this is taking a long time. To get to 200. Could I run and get a sandwich? And come back and have it still run? We're stuck on this one with this. We're building up a massive cache, and maybe that is a bit of overhead that we don't need. Like, what are the chances a specific... set of golem buttons comes up again? We're probably not getting many cache hits, so building this gigantic cache is probably costing us. let's stop. Don't use the cache. Stop using cache. And we'll also print what line number we're on as well. Let me just see. Okay, also. Okay, for line in enumerate f.read lines. Alright, we'll just use the line +1 so it matches the IDE. Alright, try this. No cache. Guess no gym for me tonight. They hadn't plowed the parking lot. Oh. Okay. Alright, so I've removed the cache. I think the cache was pointless. Let's see if that actually speeds things up. So the first one takes a while. 20 centimeters. I think this is going to take a long time. I don't know what... I've already written this. So this works. It's going to take a long time to get through all the lines. Maybe we do need to cache. But we should reset the cache per problem, because why are we reusing caches from different problems? I think that's pointless. Okay, we're getting somewhere. We're on line 9. Got to do 200. So it's the problem is when there's lots of buttons. So when the numbers are big, that's not too big a deal. The real issue is when there's lots of buttons. Like, if you're being greedy, generally you want to press the button which has the most numbers in it, because you're trying to fill this goal, and like hitting the big buttons adds more joltage overall. So maybe what we should be doing is turning this on its head and saying, take the biggest buttons and try every possible number of presses on them from 0 to, I don't know, one of these numbers. And then take the sub-problem where we remove that particular button and modify the goal. Yeah, maybe that's the better way to do it. So we're doing this partitions thing. I feel like we can also finish early when we see that we can't beat a certain target, like, so here, get optimal joltage, think we just leave this problem to run then, but... Do I just leave the stream running? Let's see. So we're on 10. 10 is taking a while. That's because it's got lots of buttons. So the problem points are going to be these ones with lots of buttons. There's lots of them. Either I just stop the stream and just let it run, and then I just like record myself entering the answer into the website and then stitch the two videos together or something. I do want to try this different approach. I don't want to stop execution now. I think the approach really, we should be greedy here. We should be going for the biggest buttons and then leave the smallest buttons for last. Like, you get the most value out of pressing a big button. So you should be doing that. What do I do? How long is this gonna... what is the estimate here? So we've completed 10, so that's like 5%. It's gonna take a long time. It's been several minutes, so... Yeah, I can't finish this on... I can't let this run to completion on stream, that's for sure. So either I stop and try a different thing, but we've proved that this gives the right answer. So I kind of just want to let it... Okay, how long is 10? Let's see how long 10 takes, because this is... If there's some which take like an hour on their own, then this is not feasible, and it's not even a good solution. I'd rather find a better one. 10 is this one, so it's like lots of tuples, but that does actually happen sometimes. Let's wait for 10 to finish, and if it doesn't, then... So I have to come back later with problem 9. Alright, I'll stop the stream there. I'll leave it running. I'll just record in... If it's the correct answer... Well, I'll record myself typing it into the website, and if it's the correct answer, that's it, we're done. I'll just upload the video or whatever. And if it's the wrong answer, then I guess we're gonna have to do another stream, aren't we? But there's no point me sitting here any longer. I need to go eat, and then later on I can try and do another stream where I catch up on problem 9. We're so behind. There's only 2 more days after this. I want the final day, we only have to do the final problem. This problem 10 is a real problem. want to see at least 10 get done. So that will give us an idea of whether it's doable. Problem 196, that looks quite nasty. That's the biggest one. No, it's not. 122 is worse. Oh boy. The numbers aren't too big though. 6, 8. Alright, there's nothing more for me to do here. Let's just stop the stream. Don't really want to raid when I haven't even solved the problem. No. Okay. Alright, well that's it for now. I'll probably come back later with a stream for problem 9 or this one if this one failed. I think this will work though. I mean, it's... I don't see anything that's fundamentally incorrect here. It's just really slow and it's just trying a lot of values. Alright. See you next stream. Bye-bye.